Your new computer wallpaper, thanks to Webb. A precise measurement of dark energy and dark matter throughout the age of the universe. Black holes twisting space-time into knots and blasting out jets that seem to be going faster than the speed of light. All this and more in this week's episode of Space Bites. Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years, and this is our Space Bites. Short, bite-sized news about space and astronomy that happened this week. All right, let's get into the stories. The pillars of creation. All right, you just gotta love the timing. We do a lengthy episode on the first 100 days of James Webb. We talk about all of the cool science results, all of the research. We show the images, the galaxies. It takes us a long time. Anton has been editing his heart out, and as we're putting the finishing touches on the episode, we get this. This is the pillars of creation taken by the James Webb Space Telescope. And many of you in the audience are now going to decide that this is your favorite picture taken by JWST so far. And I don't blame you. You know what? Take a second, update your phone background, update your computer background. This is your new wallpaper. So what is it? Now, the Pillars of Creation is a star-forming complex in a very famous nebula called the Eagle Nebula. And it's a very bright nebula. If you've got a small telescope, you can see it. If you have the ability to take pictures with your telescope, you can take pictures of it. I've taken pictures of the Pillars of Creation. They don't look anything like this. Most famously, we got the Pillars of Creation taken by the Hubble Space Telescope. And we got the first version of these back in 1995. And then we got a much better version of it several years later after Hubble had gone through its servicing mission. And what these are is brand new stars that are still shrouded by dense clouds of gas and dust. And you've got other stars in their area, and they've already cleared out the gas with these powerful stellar winds, and now they're shredding these cocoons that are surrounding these other stars. It's a very dynamic environment. In fact, astronomers think that in the few thousand years that the light has taken to get to us, that the Pillars of Creation have actually collapsed. They're no longer there because of these intense stellar winds. And when astronomers compare images from the Hubble Space Telescope to James Webb, they can actually see differences in the shape and structure because of how these winds are pushing all of this dust around. Now, the key difference is that when you look at it with Hubble in visible light, you see these dark clouds of dust that are blocking your view into the actual star-forming nebulae. And in the James Webb view, because it's infrared, because it's designed to look through gas and dust, those dust clouds are gone. And now we see right into the nebula. We see again, stars that have never been seen before. And so it's a beautiful picture, but it's also scientifically useful. And so when you put it up as your wallpaper, you can study it and do some science while you are enjoying this beautiful picture on the background of your phone or computer. Big rip? Maybe not. Now, astronomers have a bunch of ways that they measure distance in the universe. Up close, they use a technique called astrometry, and this is what the Gaia mission does when they look at the movement of background stars as the Earth and the Gaia satellite are going around the sun. At farther distances, they use this method called Cepheid variables, where they have these stars that pulsate in a way that is intrinsic to their brightness. And so if you can measure one of these stars, you know how far away it is. And this is what Edwin Hubble used to measure the rate of expansion of the universe. At the other end of the spectrum, you've got the cosmic microwave background. This is the first light that made its way out into the universe after the universe became transparent. And the problem, and you've probably heard of this, the crisis in cosmology, is the fact that when you measure the expansion rate of the universe from the Cepheid variables, which go up to a couple of billion years ago, And when you look at the cosmic microwave background, which is 13.8 billion years ago, you are seeing two different expansion rates. And astronomers have measured these with a level of accuracy where the error bars do not overlap. And so this is a challenge, an opportunity. It's quite exciting. And so in order to solve this, astronomers need other ways to measure distance in the universe. And one of the most powerful ways is using type 1a supernova. These are white dwarf stars that explode. And astronomers aren't exactly sure why they're exploding, but they do know that they explode at a very set mass, 1.4 times the mass of the sun. And so because they know these explode at a very set amount of mass, when you see one of these explosions, you know how much energy it is intrinsically, and that allows you to measure the distance. And astronomers use this technique to measure distances out to 8 billion light years away. It was the analysis of these type 1a supernova that astronomers used to discover that the rate of expansion of the universe is actually accelerating. This is dark energy. And so a lot of distant measurements in the universe really rely on this technique of measuring these type 1a supernova. And so astronomers have been collating a really precise database of all of the type 1a supernova that have ever been seen so far. The database is called Pantheon Plus, and most recently they released one that had 1,570 distance measurements to type 1a supernova. They went all the way back to those first type 1a supernova that were analyzed to help figure out the existence of dark energy, but then they've also gone and included these measurements all the way through until the most recent ones. And these are popping off relatively close by, within a few billion light years away, but also really far away. And when you think about it, like since 1998, astronomers have seen just over 1,500 of these things. They're fairly rare and very important. And so they used the best techniques they could, the most precise measurements, they normalized all the data, and this allowed them to make some really interesting discoveries about the history of the universe. It allowed them to see that at about 3 billion years after the Big Bang, this time that's known as cosmic noon, that the mutual gravity from the regular matter in the universe and the dark matter in the universe was starting to slow the expansion of the universe, and they were able to measure this ratio quite precisely. And then a few billion years later, as dark energy started to kick in, it started to speed up the expansion of the universe, this acceleration that we now know. And so we've got really precise measurements of the amount of matter, and dark energy at different times in the universe. I did an interview with one of the investigators behind this research, Dr. Dylan Brout, and that's going to be coming up in a couple of days. And we go into great detail about what's in the database, what they discovered, what they learned. But one question that I've always been really fascinated about is this idea of the Big Rip. Is the amount of dark energy that's coming into the universe increasing, decreasing? Will it lead to the universe tearing itself apart in the future? And it looks like now the analysis from these supernovae are so accurate that astronomers are pretty sure that we're not going to see this big rip in the future, that the amount of dark energy is constant. So good news, apocalypse canceled. Instead of 10 billion years left, you've got Google years left to enjoy this universe. Remember, they found about 1,500 type 1a supernova. When the Vera Rubin Observatory comes online, it's expected that it will find 1 million type 1a supernova as it operates, which will provide just an enormous amount of data. So another reason to be really excited about the Vera Rubin Observatory. Black holes tie space-time into knots. It feels like we've always known about gravitational waves, but it's been fairly recent. The first gravitational waves were detected by the LIGO Observatory just in 2016, like 6 years ago. And from that, astronomers have then made improvements to LIGO. They've added a new observatory called Virgo. There's another one coming online called Kagra. People are planning space-based gravitational wave observatories as well, called LISA. And so we're entering this era of being able to analyze gravitational waves with more care and fidelity than ever before. So we now see a merger of black holes or a merger of neutron stars or a black hole and a neutron star. These events are happening almost every week, sometimes multiple times a week now. And it just shows how what was an incredible discovery has kind of just become normal. Astronomers were studying one of these black hole collisions that happened back in 2020, and what they found was as these two black holes were starting to get closer and closer together, space-time around them was causing them to precess, causing them to shift in their orbit as they were going around each other. And we see a very calm version of this when you think about the orbit of Mercury going around the sun. The position of Mercury never seemed to match up the predictions made by Newton's calculations. And it wasn't until Einstein came along and said, oh, it actually turns out that the gravity of the sun is twisting up space-time around it. When they were able to include those calculations, the orbit of Mercury started to make sense. You've got this frame dragging caused by the twisting of space-time by the mass of the sun. But in the case of these black holes, you got one with 40 times the mass of the sun. It's spinning at the fastest possible rate that it can. Literally, it cannot spin any faster and still fit within the laws of physics. And the space-time around these black holes is twisting up and precessing about 10 billion times faster than anything that's ever been seen before. And so you can imagine the moment before these black holes collide with each other, they twist up space-time. They're turning at rates that are approaching the speed of light. And it is just a crazy environment before they actually collide and turn into a more massive black hole that then continues off into the cosmos to find more victims. The most powerful gamma ray burst ever recorded. Gamma ray bursts are incredibly powerful explosions, and astronomers now think that they're probably caused when the most massive stars in the universe detonate as a supernova. And it's funny, for the longest time, astronomers thought there had to be something really special about these gamma ray bursts because they were seeing them in places where there were no galaxies. And so they were thinking maybe there's something special about stars that form out in the voids in between galaxies. Somehow they can get bigger than normal and detonate as gamma ray bursts. And now they've been able to see very faint galaxies surrounding these gamma ray bursts. So they do form within galaxies after all. On October 14th, astronomers detected a gamma ray burst that overwhelmed their detectors. It was the most powerful gamma ray burst they've ever seen. The brightest of all time. They're calling it the boat. Based on the number of gamma ray bursts that have been seen so far, it's thought that this is like once in a century in the observable universe, maybe once a millennia. It's a pretty powerful gamma ray burst. It also seems to be the closest gamma ray burst that we've ever seen. The light left it about 2.4 billion years ago and has been traveling ever since. That seems far, and yet the radiation from this gamma ray burst had a very real effect here on planet Earth. Like I said, it overwhelmed the sensors from some of the satellites that were designed to watch it. It ionized the atmosphere of the Earth and disrupted communication systems. Wow, and that's 2.4 billion light years away. Imagine if one went off here in the Milky Way. If you like the work that we do, why don't you consider joining our Patreon? This is our members-only club where you can get advanced access to videos that we create and interviews. You can get behind-the-scenes information, and if you join as a Patreon, I will remove all of the ads from the Universe Today website for life. You can sign up, cancel right away, and you'll never see an ad again as long as you log in when you access Universe Today. You can go to patreon.com/Universe Today and know that you are supporting independent space and astronomy journalism. We exist because of people like you who think that it's important for independent space journalism to exist here on planet Earth. So thank you. Patreon.com/Universe Today. Hubble sees a black hole jet moving faster than the speed of light. Speaking of gravitational waves, this is clearly a very gravitational wave episode. Remember back in 2017 when we saw two neutron stars collide with each other, and this was the Kilonova. And what was really cool about this event was that the two neutron stars were detected in gravitational wave observatories, but then they were also seen in the sky with visible light. And so astronomers were able to measure the gravitational waves, but also study the radiation in a lot of different wavelengths. And we learned a tremendous amount from this one event. We learned that the speed of light is the same as the speed of gravity, that the gravitational waves and the radiation arrived at exactly the same time as you would expect. We learned that colliding neutron stars are probably a source of heavier elements here on Earth. They saw an enormous amount of gold and platinum and other heavier elements in the wreckage from this explosion. Of course, this was really exciting, and so astronomers wanted to make follow-up observations. And so a couple of years later, they pointed the Hubble Space Telescope at the wreckage of the 2017 Kilonova. And what they saw was that whatever is remaining, whether it's a neutron star or a black hole, it is blasting out some kind of jet that is roughly pointed in our direction. And what's really bizarre was that they detected that the material coming from this jet is moving several times faster than the speed of light. Now, I'm sure you're saying, whoa, 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 you know, nothing can move faster than the speed of light. And it's not moving faster than the speed of light. It's because of time dilation, because this material is moving directly towards us at 99.97% the speed of light. It appears, from our perspective, to be moving several times the speed of light because we're experiencing different amounts of time from the jets. It's weird. And so hopefully over time, we'll be able to make more observations of the Kilonova aftermath as it continues to evolve and spread out, and get a much better sense of what role these Kilonova events play in the history of the solar system. How much of the heavier elements on Earth come from colliding neutron stars? A warning sign for supernova. Red supergiant stars live very short lives, like just a couple of million years. And so that's why in the biggest star forming regions out there, the heavy stars just detonate quickly, they seed the surrounding area with heavier elements, and they're gone. And it's believed when one of these red supergiant stars is about to die, it dims. It's essentially shedding off the outer layers of its star, and it obscures our view, and then over the course of, say, 10 years, it builds back up and it explodes as a supernova. Astronomers have detected before and afters of several supernovas. It's happened about a dozen times, but there's always a big delay. A supernova is detected, and then astronomers look through their old archival material and go, like, does anyone have a picture of this galaxy? Can we find the star? And 12 times they have been able to find it. But the gap between when the supernova went off and when they last observed the star was still too far. And so astronomers are hoping they can figure out some kind of early warning system. There's another theory of what you might expect to see when a supergiant star is about to explode as a supernova, in that it will still dim, but it will dim a lot and very quickly. It's believed in the last year before the supernova explodes, it sheds off about 10% of the mass of the star. And this creates this big cloud that obscures our view. And it's so much material that it should make the star mostly disappear from our perspective. It'll decrease its brightness by about a factor of 100. And then within 1 year, it will explode as a supernova. And now astronomers are going to be looking for red supergiant stars that suddenly disappear, because those could be the ones that are about to explode as supernova. I talked about how the Vera Rubin Observatory is going to be finding 1 million Type 1a supernova. This is the other kind of thing that Vera Rubin will be excellent for. It's going to be analyzing the entire night sky from the southern hemisphere every few nights. And so if a single star in a single galaxy disappears or dims down within a couple of days, Vera Rubin should be able to observe it, and astronomers will know to point their telescopes at that star and watch to see if it's going to explode as a supernova. Can you imagine us watching the supernova happen in real time? I mean, obviously it happened in the past, but the light is getting to us and we're able to watch the light. All right, those are all the news stories that we had today. Of course, you can get links to everything that I talked about today in the description down below. You can also get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There, you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross who support us at the Master of the Universe level. All your support means the universe to us. All right, that was all the news for today. We will see you next week.